Hello, pre-calculus. Here we go with rational functions. Most of this is repeat from Algebra 2, so if you're confused, you can go look in the book, you can go look online, there's a lot of details for it. The only thing that should really be new here if you didn't take honors last year is slant asymptotes, but I'll talk about those at the end of this. So, to find vertical asymptotes, they should show up on the graph. These happen when you're dividing by 0. You get vertical asymptotes and you get horizontal asymptotes. Or, sorry, not dividing by 0. When you're dividing by x, you get vertical asymptotes when you would be caused to divide by 0. Obviously, it doesn't exist at that point. You get an infinite discontinuity. There are horizontal asymptotes. I think of these as values that just can't be reached. For example, just like you can't divide by 0, there's also no number that you can put in for x that will make 1 over x equal to 0. You can make x really, really big, and 1 over x becomes really, really small, but never quite 0. So, to find the asymptotes, you can graph them in the calculator. The vertical asymptotes will show up very clearly. You'll be able to see the horizontal asymptote as a sort of leveling off, but sometimes it's harder to tell exactly where that's happening. One way that you can check for it is to put it in the calculator and then look at very, very large values of x and see what's happening to y, or very, very small values of x. Algebraically, what you can do to find vertical asymptotes, look for values that would cause you to divide by 0. At those points, you'll either find asymptotes or holes in the graph. For right now, we'll talk about asymptotes, and holes in the graph will be later. To find horizontal asymptotes, there's several different methods. The one I find easiest is to compare the degrees of the top and the bottom. So if the degree of the numerator is larger than the degree of the denominator, there is no horizontal asymptote. If it's less, the asymptote is y equals 0. If they're the same, divide the leading coefficients. So this one, number 1, I just graphed it in the calculator, and then I algebraically found out where those things were. So what value of x makes this division by 0? X equals -3, and that's where my vertical asymptote is. To find my horizontal asymptote, I said, okay, well, the degree of the top, this is x to the first power. This is x to the first power, so the degree of the top and the bottom is the same. So I will divide the leading coefficients. That's this one and this one. 2 over 1 is 2. So the horizontal asymptote is at y equals 2, and plug it in the calculator and you can check. And then to actually draw it, just go ahead, look in the table and get some values, and really just make sure, check your intercepts and make sure you're on the right side of the lines, and that's good enough for me. For problem part B, x over x minus 1. What makes a division by 0? X equals 1. They have the same degree. 1 divided by 1 is 1, so the horizontal asymptote is at y equals 1. 1, 1, and then I just plotted it in the calculator. I want to add a little note here about why you can find the horizontal asymptote by dividing by the leading coefficients. Remember what this means, 2x minus 1 over x plus 3. This means 2x minus 1 divided by x plus 3. So what you could do is actually do that division. I've done it with synthetic division here. That's supposed to say -3. And if I do this division, my result is 2 plus -7 over x plus 3. So that my remainder is -7. 2 minus 7 over x plus 3 is the same as this. As the value of x gets very, very large, so for large values of x, -7 over x plus 3 gets very, very small. So as x goes towards positive infinity, this whole value gets ever closer and closer and closer to 2. This never stops mattering, this never becomes 0, but it gets smaller and smaller and smaller, so this will get always closer to 2. So that's why as x goes to positive infinity, y will always get closer to 2. And as x goes to negative infinity, the same thing happens. So that's really what's happening, is that I'm saying, okay, I could do the division, and what would matter is what this came out to be, and the rest of it would just turn into a remainder that, as x gets very, very large or very, very small, won't affect it very much. So if your degrees are the same, it's a division problem, and that's why that's the horizontal asymptote. The next page talks about the fact that all of these are based on the parent function 1 over x. And we've talked about parent functions and transformations. We'll talk about them more. But so you can see how the graph should happen and how it's a transformation of 1 over x by looking at those rules of transformation. Now, the graph of 1 over x has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. So when you transform the graph of 1 over x, these things may move depending. So this graph of 1 over x minus 1, this is basically my rules about inside or outside. 1 is subtracted here before the function is applied, so this is an inside. That means it's a horizontal change, and horizontals go the opposite of what you expect, so this shifts it 1 to the right. And indeed, where would this be division by 0? At 1. So the horizontal asymptote, no, sorry, my mistake, vertical asymptote is at x equals 0. 1 is at x equals 1. I'm sorry, I'm not quite sure what's happening here. All right, it shifts it 1 to the right, so instead of being at x equals 0, now it's at x equals 1. What makes this division by 0? When x is 1 and the asymptote is at x equals 1. It hasn't been shifted up or down at all, so the horizontal asymptote is still at y equals 0. That hasn't changed. And then the graph of it, you can get some values from the table. And pretty much just going to sketch this freehand. It goes like this, and it goes like this. That's a terrible graph, but you get the idea. For this next one, what's the transformation? Well, this is multiplication, but since the 2 is on the top, this is multiplication after the function is applied. So that will be a vertical expansion, that is, it's pulled taller or upwards, and the negative is also outside, so that will be a reflection vertically. Neither of these things actually change anything about the asymptotes. The asymptotes are still x equals 0, y equals 0. So the asymptotes are in the same place. The graph, however, instead of being up here and down here, because of the reflection, it's going to be up here and down here in quadrants 4 and 2 instead of quadrants 1 and 3. And because it's stretched taller, this is a little weird, but instead of going through this point, it goes through these points here. And put it in the graph, look at how it works, try a few points out yourself, and you should be able to get it. There you go. C, this is a multiplication by 7, so again, a vertical expansion. And this is a horizontal translation, so it shifts it to the left by 5. That means our vertical asymptote is at x equals -5. Our horizontal asymptote hasn't moved. X equals -5, y equals 0. And this point is going to be here, and then there will be a point here. And you can sketch it out. Again, please use your calculator to get a better idea of this. It's not necessarily the easiest thing to do freehand, especially while holding a camera. Okay, last one on this page. What happens? That shifts it to the right 3. That shifts the whole graph up 2. So that means we have moved the vertical asymptote to x equals 3 and the horizontal asymptote to y equals 2. There we go. We haven't changed anything else. So that lets me sketch the graph, more or less. Fine. I'm kind of running out of hand here. It goes all the way that way and this way, and I apologize. It's a terrible, terrible graph. You can do better than that, right? Okay. Okay, time for the new stuff, which is slant asymptotes. When the degree of the numerator is exactly one more than the degree of the denominator, then instead of getting closer and closer to a horizontal line, it gets closer and closer to a diagonal, that is to say, to a linear function. So, as you can see, this levels off not horizontally but diagonally, and it gets closer and closer to a line. The way to find the equation of this line, and therefore of your slant asymptote, is by doing synthetic division. So, really quick reminder of synthetic division. You put the coefficients, the constant term, the linear coefficient, that is of your x to the first, your squared coefficient, your x to the second. If there are more, you'd keep going. In this little box, you put the value that makes your denominator equal to 0. So let's set this up. The degree of the numerator is 2. The degree of the denominator is 1, so this qualifies. Here my squared coefficient is 4, my linear coefficient is 6, and my constant is negative 37. And the value that makes my denominator equal 0 is negative 4. You bring the very first term straight down without doing anything to it, and then multiply these two, put the result here. So this will be negative 16. Add straight down, 6 plus negative 16 is negative 10. Multiply these two together and put the result here. Negative 4 times 10 is 40. Add straight down, and that becomes 3. This is the quotient, and this is the remainder. So the way we would write the remainder, or sorry, the way we would write the result is it's 4x minus 10 plus 3 over x plus 4. That's essentially, not essentially, that's exactly, this is the same as this. Usually we don't write it that way though, because this is a little more complicated looking than this. So normally we just leave it like this. But what this means is that this can tell us what happens to the y value as the x value gets larger and larger. Again, the key is that as x goes to positive infinity, as x, for an example, as x is 20, this is 3 over 24, which is only 1/8. When x is 1,000, this is 3 over 1,004. When x is 1990, never mind, I was trying to do something clever, but it's not working. When x is 1,000,000, this is 3 over 1,000,004. This becomes tiny, very, very close to 0, never exactly 0. But that means that the graph of this function gets ever closer to the graph of y equals 4x minus 10. Oops, sorry, minus 10. It'll never reach it. This is never 0, but it'll get very, very close to it. So that's it. To find the slant asymptote, you do the synthetic division, and you say as x gets very, very large, the remainder gets very, very small, so you get closer and closer to the part without the remainder. We'll get some more practice about that on the back. Last sort of thing is point discontinuity. So there are times when you have a function on the top and the bottom, and you could cancel. Everywhere except when the bottom would be equal to 0, these basically don't matter. You have the graph of x plus 2. When this would be 0, this does matter. Suddenly this function doesn't exist at that point because this hasn't actually gone away. So since an x value of 3 results in a denominator of 0, you might expect there to be a vertical asymptote. Because we have the same function, or same factor on the top and the bottom, it's not a common factor, it's just a hole in the graph. So, for example, in this function here, everywhere except at 3, x minus 3 cancels out on top and bottom, and you're left with just the graph of x plus 2. At 3, however, we say, we make a little circle. It won't show up on the graph, but it will show up in the table. So when you graph it, you make a little circle to show that you know there's a hole there at 3, 5. And it momentarily disappears and then reappears. That's a point discontinuity. So this one, sort of exciting, or well, exciting maybe a bit much, but interesting anyway. Where is the denominator equal to 0? It's equal to 0 when x is 0, when x is 4, with multiplicity 2, but while that will affect the graph, it still only show up as one denominator. And when x is negative 2, but that factor appears on top and bottom, so it will be a hole in the graph instead of a vertical asymptote. And I've graphed the vertical asymptotes, and normally I wouldn't put this. I just put it to show you that this is where the hole in the graph is. And then there's the degree of the top is 2, the degree of the bottom is 4. When the degree of the bottom is larger, then you have a horizontal asymptote at y equals 0. So there's my horizontal asymptote. And then to get the rest, I put it in the calculator and graphed it. That's just a larger than normal dot. It's not a hole in the graph. That's a hole in the graph. Example 6, the graph of the rate shows a transformation, write the equation of the function. So because we know the rules about transformations, all we have to do is figure out how it's shifted and what that means for the original function. So this has been shifted, so the vertical asymptote is now at -1. So what does that mean? That means we added 1 before the function gets applied. So the bottom, instead of being x, is x plus 1. And it's also been shifted downward by 2, because the horizontal asymptote is at -2. So that happened after the function was applied. There we go. Y equals 1 over x plus 1 minus 2. Graph it yourself and see if I got it right. Okay, last note. This last page is pretty self-explanatory, but I want to remind you of a couple of things. First of all, for synthetic division, the number that goes in here is the opposite of this. It's the value that would make this equal 0. So if this is 2, it'll be -2. If this was x minus 2, it would be 2. So don't forget that. Also, you can only use this, that is, it only has a slant asymptote when the degree of the top is exactly 1 more than the degree of the bottom. Now that's true for all of these, but if it's not true, then it won't have a slant asymptote, so be aware of that. The last two on here are bonus problems. I would like it if you tried to do them, because abstraction is at the heart of understanding algebra, but these are more like the ones you actually need to do. So these 3 are part of your homework. These 2 are bonuses, and we will work on them some more in class. Bye.